Have you ever been in a packed stadium or a busy airport and wondered, why is my phone's signal suddenly so terrible? Well, the answer and the solution lies in some seriously clever engineering. Today, we're going to pull back the curtain on a key piece of that puzzle, a device called the Butler matrix.
All right, so the main challenge is actually pretty simple to understand, but it's incredibly tough to solve. Our world has this bottomless appetite for more data, faster speeds, and wireless connections that just work every time. From streaming movies to powering the Internet of Things, the demand is just exploding.
Let's make this real for a second. Think about the last time you were at a concert or maybe a crowded cafe. Why does the Wi-Fi or your cell service suddenly grind to a halt? It's because all those phones and devices are screaming for attention over the same limited airwaves. The signals all crash into each other, creating this massive digital traffic jam. The old way of just blasting a signal out in all directions, well, it just doesn't cut it anymore. Think about it like this. You're at a crowded party, and everyone is talking at the same time. It's almost impossible to have a clear conversation, right? Well, that's exactly what's happening to our Wi-Fi and Bluetooth signals. The answer isn't just to shout louder. The answer is to find a way to whisper directly to the person you're trying to talk to, cutting through all that noise. So the question is, how do we give our data that kind of VIP treatment? And this isn't some abstract, far-off problem. We focused our work squarely on the 2.4 gigahertz band. Now, that's not just some random number. It's the invisible highway that powers the Wi-Fi you're probably on right now. It powers your wireless headphones, your smart speakers, all of it. So improving this specific band means a better, more reliable connection for the gadgets you use every single day. Okay, so if just shouting louder isn't the solution, what is? Well, we have to get smarter. And that's where this really cool concept of beamforming comes in. Instead of flooding a whole room with light, what if you could aim a powerful, focused spotlight exactly where you need it? That's what we're about to do with our wireless signals. Put simply, beamforming is the art of focusing wireless energy. It's a technique that lets an antenna system literally steer its signal toward a specific user or device. And when you do that, you dramatically improve the signal strength and the quality of that connection. You know, a great way to think about it is like this. A standard Wi-Fi router is basically a floodlight. It lights up the whole room, including all the empty corners where nobody is. Beamforming, on the other hand, is like a spotlight. It follows you, the user, and delivers a much stronger, clearer signal right where you need it. And the best part? It drastically reduces the interference for everybody else. It's a win-win. So what's the engine that makes this spotlight work? How do we actually aim the beam? Well, that's the job of this little guy, the Butler matrix. You can see its intricate design right here. This is the clever part. It's the engine that takes one signal, then splits it, and phases it in just the right way to create and steer that focused beam of energy, all without any complex or power-hungry electronics. It's just smart physics. Now, of course, a great idea on paper is one thing. Turning it into a real working piece of hardware, that's a whole different ballgame. So let's walk through the process of how we took this from a digital blueprint to an actual physical board. It all starts on the computer. We used a really powerful software called Advanced Design System, or ADS, to design, simulate, and tweak every single one of these little pathways you see here. And this step is absolutely critical. It's like building and testing thousands of virtual prototypes so we can get it perfect before we ever make a single physical object. Then we move from the digital world to the physical one. The fabrication process is kind of like a high-tech version of screen printing. First, we print our design onto a film, which acts as a mask. Then we use UV light to harden that circuit pattern onto a copper board. And finally, a chemical bath just washes away all the extra copper, leaving behind our perfect, precise design. We just solder on some connectors, and it's ready for testing. And here you can see the payoff. On the left is our final digital design from the computer, and on the right, that's the actual physical board. The match is just incredibly accurate. It's always a fantastic moment when something that only existed as data becomes a real piece of hardware you can actually hold in your hand. All right, this is where the rubber meets the road. A design can look perfect on a computer screen, but the real test is how the physical device performs in the lab. So we hooked it up to find out and compared the results directly against what our computer simulations predicted. First, let's look at what the computer predicted. This graph here basically shows us how well the device is tuned. What you're looking for is a huge, deep dip right at our target frequency, 2.4 gigahertz.
And look at that. That deep valley tells us that the signal is flowing into the device almost perfectly, with practically nothing being reflected back. So, our simulation predicted a fantastic result.
And now, the real test. We connected our physical board to a vector network analyzer, which is a super precise piece of measurement equipment. And there it is. That dip you see on the screen, that's the real-world performance. It lines up almost perfectly with our simulation. This right here is the proof. Our design works, not just in theory, but in reality. When you lay the numbers side by side, they really tell the whole story. Look at the return loss. That's how much signal gets wasted. The simulation and measurement are an excellent match. And power transfer, how efficiently it works, again, remarkably close. The data is clear. This project was a definite success. We hit our goals.
Okay, so we've proven the design works. The numbers check out. But what does a successful Butler matrix really mean for people? Let's connect these technical wins back to the real world.
So what does this all mean for you? Well, for one, it means less interference from your neighbor's Wi-Fi network. It means a stronger, more stable connection for your phone or laptop because all the energy is being sent right to you, not wasted. And since we built this using standard, low-cost circuit board material, this isn't some expensive, futuristic tech. And maybe the best part? The exact same design principles scale up perfectly to power the next generation of 5G and even 6G networks.
You know, this quote from the original research paper really says it all. This project isn't just some one-off experiment. It's a building block. It's a real step forward in creating the kinds of advanced, efficient networks that are going to power the next generation of wireless, everything from 5G to whatever comes after that. So here's the real takeaway. By figuring out how to make these beamforming components on low-cost materials and proving that they work this well, engineers are making this advanced tech way more accessible. And that helps pave the way for smarter antennas, faster networks, and just more reliable connections for every single one of us.